we'll just go directly on to Conny Aerts, the last of the laureates of today, who has brought asteroseismology to stars very different from the sun and also different from those we heard about now at the end of Jørgen's talk.
1, 2, 3. Is this on now? Yeah. Okay. Thanks a lot. I'm extremely honored to be here, but I'm going to ask you to buckle up because we're going to go to higher speeds. That's to save your lunch, but also because I like higher speeds. Okay. And I like it hot, as Jørgen said, right? So here's a map of stellar evolution. You just heard that our knowledge of stellar evolution is a bit rusty. We hadn't anticipated that, and sometimes people who do stellar evolution are not so happy when they see astroseismologists coming, because we sometimes bring inconvenient truths. But the stars do what they do. They are right, and the theory is wrong, whether you like it or not. So Roger and Jørgen have done, like, say, the left part of this diagram, the sun, solar-like stars, and solar-like is more or less the same mass, right? And convective outer envelopes that create acoustic modes, and then when they evolve, also mixed modes. I'm going to be here for the next 20 minutes. A bit less, I will try. And why is this interesting? There are far fewer stars on the right of this diagram if you look in the number of stars, because we have distribution according to mass, but they are much, much more important in terms of chemistry, and we should thank them, because feel your skin, feel your jewelry. That's all made by stars on this side. So chemical evolution of galaxies is really created by massive stars. And for me, massive, that means anything that has a mass higher up of, like, typically 1.3 times the solar mass, so that's fairly low still, and all the way up, where we can detect oscillations. Why? Because these stars have not convection in their outer envelope, as has been explained before, but convective motions in their inner core, where the nuclear reactions are happening, right? And that means that the physical description, these models need a different description than solar-type stars, okay? Now, I have to care about rotation, and that's why I'm saying higher speeds, yeah, because massive stars are fast rotators. And if you have fast rotation, then you cannot avoid to mix the material. You rotate around, think about your cup of coffee, you pour milk in it, you don't wait until the mixing is complete, because your coffee is cold and it's no longer nice to drink. No, you take a spoon and you give angular momentum to your coffee cup. You don't think about that probably when you do it, but that's what you're doing. And so when you have fast rotation, you mix material, and I have to care about that a lot in the inner regions of massive stars, right? So chemical mixing is very important, and it is coupled to the rotation in the place where the nuclear burning is happening. Yeah, so that's a bit of a cartoon-like picture. Now, as I said, I think this is the playground that Jørgen was shown in another type of diagram. I've simplified it. So we detect stellar oscillations from about 0.7 solar mass stars all the way up to 25. So here's the sun, and Roger and Jørgen basically did this part of the axis, right? A bit higher. But we go all the way up to 25, and as of stellar mass birth, say 9 solar masses end up, stars will explode as supernovae and give all their metals to the environment. Yeah? In terms of ages, let's say, we cover from about 10 million to 10 billion years. And the higher the birth mass, the shorter the life. The more violent the fuel is burned, let's say. Okay? And then critical rotation, what does that mean? You know, you have very slow rotators like the sun, and you have very fast rotators. But if you go above a certain limit, then your rotation is so fast that the centrifugal force tears your object apart, and you don't have a star anymore. That's what we call critical rotation, right? And so my playground here is really this full axis, right? Very fast rotation and also very slow rotation. in these stars. Now, that means I'm in a more difficult mathematical regime of the frequency. So here's a very simple diagram. The oscillation frequency, and Roger and Jørgen are here to the right. Okay? Well, going a bit, well, also a bit here with the mixed modes. But still, yeah, the rotation frequency, the rotation of the sun is about 27 days at its surface. You have seen the map of the inner rotation. It's all very slow for me, right? My stars have rotation periods like typically a day or so, and they are much bigger. Yeah, so it's a very different regime. On the other hand, the oscillations in high mass stars can also be acoustic modes. Yeah, they are bigger musical instruments. So instead of 5 minutes, you typically have like a couple of hours for the largest stars. But we also detect pure gravity modes, and they have very low frequencies, right? So if you have low frequencies and fast rotation to combine, then you cannot afford to ignore the Coriolis force and the centrifugal force. You have to take that into your mathematical description, okay? And that's the big challenge that we face, okay? So for Jørgen and the crowd, let's say, rotation is happening. We see that in the sun, in the solar type stars. Magnetism even, that's a fantastic new discovery that was announced several weeks ago at the Leuven meeting. But it's still small effects compared to the forces of gravity and the pressure that sets the scene of the dominant acoustics. Here, I'm here with some of my stars where the frequencies of the oscillations have the same order of magnitude in terms of periodicity than the rotation of the star. And so then you can no longer pretend that the Coriolis force is just a small detail. No, it's dominant, right? And that's a challenge. So my stars are all over the place, right? In terms of probing power, I have this, what we call a propagation diagram. So frequency on the y-axis versus depth inside the star. Yeah? Acoustic modes are probing the outer layers, the convective envelopes in case of low mass stars. Gravity modes sit here all over the place, and the nice thing is they are more complicated to understand, but they probe right into the inner core next to the convective core of the star, and that's what sets the life of the star. Yeah, so that's a benefit, but you have to do more effort, right? Now, here's my favorite star. I have to show this star because that's probably why I'm standing here, thanks to this star. Yeah, maybe. This is a massive star long before we had space missions, and so that has acoustic modes, but it takes several hours instead of 5 minutes. And you want to have many, many modes, so as much as you can. So you have this whole beating pattern in the data that you have to cover, but you can only do it at night if you are lucky and the weather is fine and you have no technical problems. So in order to unravel more than one mode, not zillions of modes like these solar people can afford, yeah, it took us 21 years of data gathering to find 6 modes. My supervisor started with that. He gave up after 10 years, and I was too stubborn. I'm a bit stubborn sometimes. I continued without telling him that I was using his telescope time. And this star, then all of a sudden, in a Christmas break, revealed 6 oscillations. 6! And that allowed me to derive a lot about this star. Yeah. What did we find? Here you see the 6 modes in full lines. Here the amplitude as a function of frequency. And I work in the units per day. Why? Because that's much more convenient. And it's like euros and your national currency. Doesn't matter. What you see here is beautiful rotational splitting. So here is a dipole mode split in 3, and here is the color-coded version of the identification of these modes. Here is a radial mode, and here is 2 parts of a quadrupole mode. So if you have rotation, then you split the sound across frequencies. You know that from a musical analogy, right? And so we actually do music of the stars all the time, right? And this splitting here, you can't see that by eye, and this one here, it's not equal. And this mode probes more the inner region of the star, and this mode probes more the outer region of the star. And so what we have an unequal splitting, and that allowed us to deduce differential rotation in a star other than the sun. That's fantastic. And so that made me shout in my house. And that's the story in my autobiography, because my daughter was stirred, and she said, "What are you doing? You're shouting." This point and this point, this gives about between 3 and 4 times higher rotation frequency in the internal layers than the outer layers. And so you expect, as Jørgen explained, the cores to spin up as the star gets older, because the envelope expands, you slow down, and the inner core contracts. So pretty good in terms of theoretical ideas. 21 years is not something you want to repeat, because you can do 2 stars in a career. This is not very exciting as an outlook, so I was lucky enough to team up with Gerald Handro from Poland, and we started setting up multi-site campaigns to break the gaps in the data, because that's a killer for us. Yeah? And we did a few multi-site campaigns. You see here the outcome for one of them, for the star 12 Lacerta in this case, a similar star than the one that I had found, because of course if you have one star you want to know, is this typical? Is this exceptional? How does that compare? And I think it's fair to say that Belgium and Poland sort of led that type of work. Tens and tens of astronomers working months and months at telescopes around the globe to get a few frequencies. Yeah? Better than a single site campaign of 20 years, but still. And so the summary of that until today is here in this graph that was made by my student, Simon. Central rotation compared to envelope versus the effective temperature of the star, depending on how hot they are. And you see very few stars. 1, 2, 3, 4, 5 stars in 20 years' time, right? That's not a great deal. And you see the differentiality of a rotation. So 1 means the same rotation frequency throughout the star. And it's not happening in these stars. So they are differentially rotating. And that's pretty well in terms of theoretical comparison, but the error bars are large. These are all stars that will later explode as supernova. They have high masses. Okay. But then we were so happy with these satellites, not only for the cool stars, but also for the hot ones. And we started also covering the mass regime between 9 and, let's say, 2 solar masses. And these stars will not explode as supernova later on, but they have very deep, high-order gravity modes of very low frequency. And you see beautiful picture here, 7 stars with the beautiful data, uninterruptedly. You cannot imagine what joy we had, thanks to the satellites. And here you see their power spectrum overplotted in red. And you see that you sort of have an evolution here. And that's from a very slow rotator on top to a very fast rotator near critical rate, this star, right? And so when you have increasing rotation rate like that, you have increasing complexity in the modeling, as I explained before. Yeah. So we really cover all these ranges. Yeah. Now, how does that work? You have gravity waves, and so when you have rotation, then your waves either they go along with the rotation or they go against the rotation. Yeah. Let's take waves, modes that go along the rotation. It means that for us as an observer, when you go along, well, then you occur faster in the line of sight as if you were not going with the rotation, right? We call these prograde modes. Yeah? So they come faster. So their periods for an observer are a bit shorter compared to the non-rotating case, right? And what we have as a diagnostic diagram is a bit similar to an Echelle diagram, but we work in periods because the frequencies are low. So 1 over the frequency, which is the period of the mode, is high, yeah, is long, slow modes. We measure difference in period between modes of consecutive overtone, if I were to translate it in musical terms, right? And then we plot them against the period of the modes. Yeah? So if you have a prograde mode, your periods get shorter, and if you subtract two values that are smaller, then the difference is smaller. So what does rotation of gravity modes do? It makes you go from a straight line tilted towards the left in this diagram. So if we can only measure this, in reality, this gives us an immediate handle of the rotation of the star, right? And where in the star? Next to the convective core. That's fantastic. Now it's obvious, but we didn't realize it until we saw it. That's always how we discovered it. So do stars do this? Yes, they do that. And here you see an example. One star where we have the data on top, amplitude spectra, and then this period difference versus period of the modes. And each red dot here is a measurement in the Kepler light curve. Okay? And you see it's tilted downwards. That's prograde modes. I find that fascinating, but every day I go to work, right? Because we're looking in the deep interior of stars, hundreds of parsecs away, not the surface, the deep interior next to the core. And we just measure the rotational frequency by measuring the slope in these data, right? That's very powerful. I could not have imagined we could do that. And this star is even more fantastic because here you see it going up. What does that mean? That the waves, they are retrograde. They go against the rotation. It takes a bit longer before it comes in our line of sight. So longer periods, if you subtract two bigger numbers, your difference is bigger. So upward slopes are retrograde modes, right? And so this is a star that is slightly more massive than the Sun, like typically 1.5 solar mass. This is all new, and this was derived by my PhD student at Timothy van Reet. But the nice thing is we have a sample of such stars where independent teams, because this is all brand new, this is what we call gravito-inertial astroseismology, which means that Coriolis force and the forces of gravity have their interplay and are equally important as a restoring force for the modes. And so various teams have now done this research independently because it's so new and we don't have the Sun to calibrate. We don't have a good calibrator, so we have to compare with each other, let's say, and see the beautiful agreement. And these are hot B stars, again by my student, Mai Pedersen, raised in Aarhus at master level and graduated at PhD in Leuven. Several stars, yeah. The light colors are the data, and the darker colors are our best models. Pretty good, pretty good. And all sorts of prograde modes, fast rotation, less fast, less fast, less fast. Retrograde. You see? Stars do it. I find that amazing. And so here's a summary I made of all the stars where we have core or near core rotation on the y-axis, and then as you go from here, the young stars, and they go there as they grow old. And Jørgen's stars are here. These are the red giants with the mixed modes that he showed, many of them, assembled by lots of people, and I've highlighted those who contributed, let's say, most stars in this diagram. And here are my stars. Very fast rotation, you see, up to critical rotation in their early life. And somehow, this couples back to what Jørgen was saying, they lose angular momentum, and we don't understand how that works. If there's one thing that astroseismology has taught us, is that we do not understand the theory of stellar rotation, which is not such a fun message for some people, but I find that great, because if it would just have fitted, then it's boring, right? We have to fix this. And what is important in this graph for me is that Charlotte Gérin, in red here, Timothy van Reet, and Gang Li, you see that name before, these were 3 PhD students. So for the youngsters in the audience, there have been major contributions by young people in the community, and I like working with young people. So in the early life of these stars, these stars will all evolve to these stars, right? And they have to get rid of angular momentum. And these stars have almost a slight level only of differential rotation, right? So in contrast to my most massive stars that I showed, the ones with intermediate mass, as we call it, between 1.3 and, let's say, 8 solar masses, as it happens, we see in the data, and we really probe the deep interior, that their rotation of their convective core, as they grow older, you expect it to be much faster than the surface. It doesn't happen. Real stars do not do that. It must mean there is a stronger coupling between the convective core rotation and the outer layers of the star, because they are not spinning up as fast as we had planned them to do. And there is a factor up to 100 wrong. Not just a tiny bit, 2 orders of magnitude wrong. And we are trying to fix this. And for fixing it, so far the models say, okay, we have 2 groups of models. The waves perhaps evacuate angular momentum, or there's a magnetic field. And that's why I'm so happy with this new discovery of magnetic fields, right? Now, the good news is also when we measure this tilt, we can measure the rotation frequency. And then we, of course, want to estimate masses and radii, and we can sort of do it in 2 steps, thanks to the measurement of these slopes. Yeah? Now, so we have the space photometry. For us, doing massive stars, it's probably fair to say it's more critical that we need luminosities, and we can do that nowadays from space astrometry, and spectroscopy, because we need to understand the chemical composition at the surface, and then check if it can be the same in the interior. So you have the seismic data, you have the identified modes, observations, and then we go to our theory. And in massive stars, as you will have understood by now, we have rotation, magnetism, convection, and chemical mixing. We have to care about these things more than in the low mass stars. And then we compute stellar models, and I call them simple. Why? Because we are assuming up to the present day, for the past 50 years, 50, that stars are gaseous spheres. And when you rotate near to critical, that's not very good. But it's already so much more complicated to treat the rotation and the Lorentz force. And now, basically, our models tell us, nah, we are not spheres. Well, the stars tell us. That's why I call it simple. So you get to theoretical predictions, and you can compare, and we do that with statistical, mathematical statistical modeling, with proper error estimation. So we can find masses and radii of stars. Not only that, also core masses and core radii. And you have to know for these stars how much material is in the convective core, because it's fully mixed. And that sets the amount of material that can take part in the nuclear reactions. Yeah? So we can do that for so-called F stars. So these are between 1.3 and 1.9 solar masses. Here, a number of stars that we have, the best known stars in this category. Few, not the thousands that Jørgen showed of the red giants, but we are working on it on a daily basis. So the ratio of the convective core mass to the total mass of the star is plotted here as a function of the age of the star. And so what is plotted here is the central hydrogen composition versus what it was born with. So the longer the star had the opportunity to burn hydrogen into helium, yeah, the more helium you make, the less hydrogen you have in the core. So this is the age axis of the star. Okay? This is young, this is old. And you see that these stars, well, their convective core shrinks. And that's what we more or less understand from stellar evolution theory, so that's good news. And here you see how the masses of the stars themselves are distributed. We also have that for B stars, fewer of them, and so these stars are much higher in mass, but they're still intermediate mass. And so you see sizes of convective cores versus masses of convective cores. We can measure that nowadays, which would be unimaginable 5 years ago. Unimaginable. And so that's, I think, the major contribution that we have brought. There are 2 red stars here. Again, we don't have a good calibrator like the sun, so we need different teams to do these analyses, not just 2 or 3 teams, hopefully many more, but it's not so easy to jump into these fields. And so these, I want to acknowledge Chinese colleagues who are trying that. You see, these 2 red stars have been analyzed by Chinese collaborators, and that's thanks to the Aarhus team. I keep repeating that they give the data away to everybody and welcomed everybody to work on it, which is a fantastic achievement. And I still want to stress that every time I talk. But you see here the Chinese modeling does not include the Coriolis force in full like we do. And so you can only apply it to slow rotators, okay? And that's what you see here. Here are the slow rotators, here the fast ones. Remember I said the faster the rotation, the more you mix, the more efficient? It's not what stars are telling us. Because the referee said, well, this is an outlier. The Leuven team has it wrong, right? But here are pretty fast, pretty slow rotators, and they have high levels of mixing. So I don't think it's Leuven. I think it's the stars. Yeah, that means that chemical mixing is something we also do not understand well. It's not only rotation that mixes the material. There are other physical phenomena. And which ones they can be? Well, you have atomic physics that also creates mixing, because heavy elements tend to sink and light elements tend to levitate. But there's also the radiation pressure that helps you to levitate even heavy matter, let's say. So we are now trying to include this atomic diffusion into our models, which is very, very hard, but we have to, because the stars tell us. And it's not just once. If it were just this outlier, it's not an outlier. We know that now. Okay, let's move on to the future, and Jørgen already said that, so that I will round off. Future directions, we need more data. You saw samples of like 40-ish stars, F-type stars, in the temperatures like 7,000 degrees at their surface. We have like 30-ish B stars, but we have a whole variety of internal physics that is much more diverse than we had planned to detect. Yeah? We need many more stars. We have data of many more stars, but the challenge in my field is you have to be able to label the modes. It's like Roger, how we had to label the modes. Yeah? And for massive stars, this is very difficult, and that's a showstopper. So we need bigger samples. The Kepler satellite omitted the highest mass stars. Why? Because they are a nuisance for exoplanet hunting, and that's what funded the mission. So I have to be a bit patient. And that's what Plato will do better, because it's the first mission, it's a big machinery that we are building to be launched end 2026. So data as of 2027, we are optimistic. And that will look at way bigger parts of the sky for a long time. So it's really something we look forward to. But what we have learned, above all, yes, we are looking forward to these new data, but none of the Kepler stars that we have is well explained up to the level of the data. So I would say the bigger need is modeling and better theory. And so that's something I would really like to work on. And what do we need to do? Well, we need to abandon spherical symmetry. And as a mathematician, it makes you a little bit sad. Because, well, sad and challenged at the same time. Symmetry is beautiful in mathematics. But stars that rotate near critical really look more like such type of object. That's not a sphere. And we have to include the centrifugal force, whether we like it or not, if we want to do a proper job that brings us up to the level of precision of the data. Now, this is not just like, okay, let's make it a flattened star, a spheroid, as we would call it. Yeah, that sounds simple, but it also comes with a complexity in the observational side, because all of a sudden you have to care about how you look upon the star with respect to the rotation axis, right? Because if you look, you know, at the, let's say, polon, if this is the rotation axis, yeah? So if your star is flattened, the poles are hotter because it's closer to the inner parts where it is hotter. And the outer layers at the equator are further away, so they're cooler. And you have to care about this inclination angle, as we call it. Yeah? You don't have to care about that for a spherical star. So it sounds easy to do this additional complication, but all of a sudden, instead of one spatial coordinate, of each fluid element inside the star, you need 3. You also need its longitude and its latitude. And so that's an immense mathematical complication. And that's actually the reason I wasn't here on Monday, for which I deeply apologize. I want to get funding to do this. And I was defending my projects to have brain power for the next several years to do stellar evolution of flattened stars, which is an insane thought, but I'll still try it anyway. And now to end up and to wake you up for your lunch, you know, we do the music of the spheres, but we haven't heard any music today. And I like giving public talks and making you involved. So I'm now going to pretend that I'm going to put you in the middle of my massive stars with low frequency gravity modes active, but your hearings are not very cooperative because the audible range of us human beings doesn't comply with the frequencies of the modes. So we cheated a little bit, but we shifted the symphony of these stars with a factor 8.6 million, and then you can listen to what it would, how it would sound if you were in the middle of these stars. So I'm gonna show an animation and let you listen to that, and then, well, you can discuss it over lunch whether you like it or not, and whether you are happy or not that there's no medium between us and the stars, because else we would be hearing that all the time. Okay, I'm showing 3 parts. The first one is the dipole modes, the simplest ones that we have of gravity modes, then 5 quadrupole ones, and then some 3 real stars whose symphony dominant modes you can hear. So here we go. Here's your symphony. So these were 3 dipole modes, shifted by rotation, into prograde, zonal, and retrograde. These were quadrupole, and now we're going to listen to 3 real stars that we analyzed. So they sound, each of them, slightly differently, and that's great news, because each one of them is giving us a piece of the puzzle of internal physics. And I thank you for your attention. I keep working on this. I'm a little bit younger than my predecessors, and I want to understand how these stars rotate, how they have magnetism, and how they mix their material. I have 10 more years to try and find out. Thank you very much.